All right, so it's been just 1 week, but I guess we have to repeat all of these things again because otherwise you just lose track of what we've been talking about. So we talked about this kind of reinforcement learning framework, and we were introducing a simple model, the Rescorla-Wagner model, right? And we were using a simple experiment to test this kind of learning process. So we show participants two random options and random and also meaningless, just abstract symbols. So then the participants make a choice and then they receive the outcome, and then they will choose one of the symbols one more time, but this time they could be able to use the previously observed outcome information to update their belief, to update regarding which one they think will lead to a reward and which one is not so, right? And we are trying to model this process using a Rescorla-Wagner value update rule. So the simple update rule is written here. So the new value is the value of the option. The value of the option, the new one is updated from the old one with a learning rate weighted reward prediction error. And what is the prediction error? Again, the prediction error is the difference between the actual reward and your expected reward, what you think you will get. So the prediction error can be positive, can be negative, can be zero. So when your actual reward, your actual feedback is better than what you think, it is a positive prediction error. If your actual observation, the actual outcome is worse than what you expected, then it is a negative prediction error. If your observation is the same, no difference relative to what you expected, then the reward prediction error is zero. So no error in terms of the prediction. And after the values are updated, and we have the value of the blue option and we have the value of the yellow option. And we have to translate the values of the two options to action probabilities. Because if you were thinking the entire modeling idea also as what we did for the coin flipping example and also for the globe tossing example, we are trying to link between the known and the unknown, right? If we are doing this globe tossing example, the globe tossing experiment, we had 9 times of experiment and 6 times of water. Those are the data. And there is an unknown proportion of water covering the entire Earth, and then that is the unknown parameter. And we are trying to make the connection using a proper likelihood function. And in that particular case, that likelihood function happens to be a binomial likelihood function. And then here, the idea is pretty similar. So we have the data, we have the choices from the participants, and we have the reward, the associated, the corresponding reward of the choices from the participants. And we have the unknown parameters in this case, like we have the learning rate here, and we also have something like determining the action probability. So how action values are translated to action probability here using a softmax function, if you remember the S-shaped, sigmoid-shaped curve. And then eventually what we want to make the connection, right? We want to make the connection between the known and unknown. So how do we decide which statistical distribution we would like to use to establish the likelihood function? And if every piece is clear here, I hope so. So then we will be able to write down our models in the STAN language. And this is the model estimation, right? And also recall the idea that we are having 2 parts. One is the R part, the big R part, and then the other one is the STAN part. And in the R part, we prepare our data in the data list, and then we send our data to the STAN model. And the STAN is the language where we will write down our cognitive model or statistical model, feed the model to the data, and let the data and the model to work together, which basically means model estimation. And then using MCMC, right, Markov chain Monte Carlo. And after the Markov chain Monte Carlo is finished, the MCMC samples will be returned back to R. And what we can do is we analyze the samples, either draw inference or like make some nice figures, plots, so that they can be used in publications, in papers, so on and so forth. Okay. So what we can do now today is a little bit more practical. And I would like to show you how to code a simple Rescorla-Wagner model in the STEM language, as we did earlier. Like we just open from scratch a empty script, and I will write down like line by line how we could build a Rescorla-Wagner model for one participant. And why we are doing this for one participant, it is because this is simpler to explain, to illustrate the code. And usually we do have multiple participants, right? We just don't run the experiment only with one person. We run experiment with multiple people, participants. And then after understanding coding the model for one person and switching to coding the model for multiple participants, it is easier, okay? I'm not saying that a experiment with one person is not valid. So maybe experiment with one healthy person is not so much accepted, not really so. But you know, there are cases where we have rare diseases, right? We didn't talk about that here, but so in my other seminar in the bachelor's pro seminar, like decision neuroscience, so I was talking about some brain lesion patients. So their brain is damaged for whatever reasons, either for generic reasons or maybe for some external reasons. But for whatever reasons, some part of the brain is damaged, so it's not functioning. Especially for those patients where there's a generic reason. So this happens with only a small percentage, maybe like 0.01% like percentage of the base rate. So pretty rare. And in that case, if you find one person or two, that is usually more than enough. So in this case, in the clinical journals, clinical studies, this is called like single case studies. Single here doesn't necessarily mean just one person, one patient, can be two, can be three, but a few, not so many. 5 is quite a lot for really rare diseases. So maybe you've heard about something called Upa-Vita patients, like they have amygdalas. Amygdala is a like area in the midbrain. So these patients, they have amygdala damaged, and this is usually a super rare disease. And I've seen papers, they only studied 2 patients, 2 this kind of patients, and they publish in good journals because this is rare, right? You can't really find that many as we usually do for studying healthy human volunteers. Okay. Anyway, let's just turn to this Rescorla-Wagner model. So we have again the choices, choice options and choice and outcome. As we did also for the globe-Thomson example and also for the regression model, we had a graphic illustration of the model. So here is a better way to help you, I guess, to illustrate what is the elements of the model and how everything is connected. So if you remember the meanings of this nose, like circle and square, and with the color shading or without the color shading, what do they mean? Well, maybe one of you could tell me if you remember, what do they mean? So circle without color, what is that? Anyone? No? Or square? Or anything, any part of them? Do you know what do they represent? Just to remember the idea of the graphic illustration of the model? Okay, I guess not. Okay, good. So we had a way to like categorize using this kind of symbols, icons to categorize our variables. And we have 2 dimensions. One is, do we have continuous and do we have discrete, right? And the other one is the data, is the variable known or unknown, okay? So if it is continuous and known, so then we will use a circle and then with the shaded area. And if it is continuous but unknown, we just use a circle and without the shaded area, okay? And for discrete, we use a square. square. And if it is known, then we use a shaded area square. And if it is unknown, then nothing is there, no background color. Okay. So this is how we try to better understand a type of the variables. So here, what is that? Circle without background color. So this is this category. That means continuous variable unknown, right? Which is basically our parameter. We don't know the parameter, but we know that the parameter is a continuous variable. Similar here, this is a circle without background color. That is a continuous variable. We are trying to estimate the parameters from the data. So here we have these squares with the background color. It is this one. This guy is discrete variable, but known. So we are knowing that they are the observations from the participants, that the reward and the choices. We do experiment, we have the log files and where the data is saved, like either in a text file or Excel sheet, or like comma separated file, it doesn't matter. Great. And what else? We also have like this V and the P. So what are they? So the value here, the V is basically the value, right? Here you could also see there's an arrow pointing to itself. This means there's update because we do update our values on a 12 by 12 basis. And how the value is updated, we just go back to the equation. The value is updated by a learning rate weighted reward prediction error. So learning rate is here is influencing how the value is updated. And whereas the prediction error is not directly depicted on the graph, but it essentially means the difference between R and V, okay? And what is the P here? The P is the action probability resulted from the Softmax function. And the input of the Softmax function is the value, action value. The output of the Softmax is the action probability together with the tau parameter, okay? So this is the tau parameter. Okay, good. And there's a question, is the tau another notion for the beta parameter? I think I never told you there is a beta parameter, right? I think I always use the tau. But some people use beta. Maybe that's the one in the paper. Is that right? Yeah, inverse temperature. Yes, yes, yes. So the tau, it is indeed the inverse temperature parameter. Yeah. Did I mention that any time? Did I use beta? Or you learned from somewhere else? Roman? Okay, yeah. Good. Right. So when we have this graph, the graphic is nothing more than these two lines, okay? These are equivalents. But maybe reading the equation is not so straightforward and reading the graph is better. I do personally believe reading the graph is better for educational purposes, so that if you are learning that for the very first time using and or seeing this graphical illustrations is helpful to you for you to have a better understanding to see well, how and which everything is connected. Great. And because we are doing Bayesian statistics, we need to have priors of all of the parameters, right? So here we have two parameters, alpha and tau, and these two parameters, we need to specify their prior distribution. So here for the learning rates, it can just be a uniform distribution between 0 and 1, and then tau is another uniform distribution between 0 and 3, okay? And you might wonder why, right? Why we use lower limit of 0, upper limit is 1. So here y lower limit is 0, upper limit is 3. So for the learning rate is actually easy because the theoretical definition of the learning rate is already quantifying that the learning rate is a parameter between 0 and 1. So we just say a uniform distribution. It does have both the limit, lower limit and upper limits already from the theoretical perspective. So we just take it as the ground, as the foundation. But for the tau parameter, theoretically, that says tau has to be a positive parameter only. Positive is just the only constraint. It has a lower limit to be 0. Theoretically, it doesn't have an upper limit. But for practical reasons, or also from empirical studies that we have seen over the, I think, 20 years, the tau parameter, we have a good knowledge and we have a good sense of what a upper limit of tau can be, okay? So most of the cases, and the upper limit of the tau parameter is 20. So if you look at papers, many of them, they use 20, or some of them, they also use 10, and occasionally they use 5, okay? 3 is rarely used, but why I use 3 here is just because I was a little bit lazy when I was preparing this kind of exercise, and I used 3. But for practical reasons, actually, usually we could use those 3. We could say 20, okay? When we are coding that in the next few minutes, let's use 20. Maybe I will just also change this one to 20. That's easier. All right, so this is the model, and this is everything that we need before we code our STAN model. So essentially, and this is the graphic illustration, and this is the illustration from the equations that you will see from the paper. And then this is the code that we will be coding. We will code a little bit. So if I show you, if I explain everything to you here, I guess that just doesn't make so much sense. So what I would do is I will just show you from coding that in R, and coding that also from scratch. So if you are doing this at home, if you want to do that, we have like multiple folders, and now we are in the 06 folder. As usual, we just double click on the R project shortcut, which will open R Studio, where the working directory is already the path of this one. Because this is located here, if you double click, R Studio will be opened directly from this directory, this path, okay? Great, and then this is R Studio, and we know that, everyone knows that. Larger, good. Use another screen. This is larger, okay. So we haven't seen R for a while, and this is the console, and this is the work space where the variables are saved, are temporarily saved in the memory. And here's the folder structure. And we have always all of the subfolders, the data outputs and the plots and scripts. So we don't have to worry too much about that because we just want to create an empty script, right? And what we can do is we save it in the script folder. We say my first rw.stan. So rw means Rescorla-Wagner, okay? .stan. And what do we have in this case? Does anyone still remember how do we start usually? If we want to write a code STEM model from scratch, where do we start? What is the first thing we write? Imports what? It seems like you're a Python person. Okay. But I see what you mean, but this is not something we start with. So this is the STAN file, right? You are talking about loading the package to the R environment, but this is done in the R main file. It is not done in the STAN script. Organizing, Martina is saying organize the data into a list. And this is also something we do in the R file, but we are now in the STAN file. So we have two parts, R and STAN. We load or import the library, the package, to the current R environment in the R file, and we also prepare the data into a data list in the R file. But now what we are here, we are in the stand file. We just are writing we are writing a stand code from empty, from nothing. We are here. And here we don't have to do the importing or loading. We don't have to prepare the data, because at this point, we are assuming that the data is already prepared from R, right? From a different place. Yeah, okay, so you see what I mean. Define the data, So Stan is a block-based language, right? So do you remember the names of the minimum required blocks? Yes, great. From Charlotte. Those are the required sections or blocks, right? Parameters. The empty blocks, just building the structure, the skeleton. Yes, that is indeed what we are trying to do. Great. So we write down the blocks. And then what we can do here is we just build the model from the beginning to the end. Okay. Let's just start with the data. So what are the data? The data are essentially the choices and then the reward, right? The outcome. And how did we name our data? I don't know at this point, but let's assume that you are already prepared. You have already prepared everything regarding your data in the main R script. And you have already prepared a data list in the R script. And what we can do is we just borrow the names that you have already done. And then we use the same name in the data block in the stan file. So if you're doing this at home, like there are actually multiple R files that you can look into. Actually, we will be focusing on this one. Okay, I will just leave this line here. Good. If you open that one, you will in fact see these a few lines. So there's a data. It's already a R data file. And now with a few things, we prepare everything into a data list. Okay. Maybe we can take a look at the data a little bit more one by one. So when we load the data, we load it, which is loaded. What appeared in the workspace is we have this guy. We have this guy. It is called RL_SS. Okay. So RL_SS, we just type down the variable, the name, and then let's see what is there. It looks like this is a matrix and it has multiple rows like lines until 100. This essentially means 112. And it has two columns. And the first column, you see the numbers, they are 1, 2, 1, 2, right? They are the choices, blue, yellow, left, right, 1, 2, 1, 2. Another column, the second one is 1 minus 1, 1 minus 1. That is the outcome, the reward. So positive feedback versus negative feedback, okay? And we also want to like soft code it a little bit. We want to see like, we don't say, instead of saying where a number of trials equals 100, we just want to derive the number of trials from the data. So here, the first dimension is 100, and we just input this number as the number of trials. And when we have all of them, we put everything into a data list, okay? So now the data list has 3 subdomains or subfields. So one is called untrials, the other one is called tries, and then the third one is called reward. Those are the names that we need for the stem file, okay? So what we do is we just write them down, right? Untrials, semicolon, because we always need a semicolon for when coding in stem, tries, and reward, okay? Reward, good. Anyone remembers what else we can do here? This is not complete. There is a complaint here. It will say something, but I don't want to show you. Anyone remembers what else we have to do so that the error doesn't appear? So whenever we declare any variable, what do we have to do? Yeah, we specify the type. Yes. Yeah. And n trials, what is that? N trials is the integer, right? Because trials can only be 1, 2, 3, 4, just integers. And choices, they are also integers, 1, 2, 1, 2. And the reward, 1 minus 1, 1 minus 1, also integers. So all of them are integers. Great. And this seems fine so far, but maybe we also have the ranges, right? Maybe we all have at least one trial. And also to avoid misspecification in the original data list, maybe because of typo, you said you have minus 100 trials. But this is to prevent that from happening, because here you are saying your data here, n trials, this variable has to be at least 1 or 2, 3, 4. Anything larger than that, that is okay. Great. And for the choice variable here, and we don't have one choice, we have multiple choices. In fact, we have how many? We have that many trials, right? We have that many choices, the same number as the number of trials. We have, if n trials equals 50, then we have 50 trials. If n trials equals 100, then we have 100 trials. Reward, similarly, we do the same. So number of trials, we have that, not that many rewards. It has to be that these two, the length or the dimension, they have to be the same, because you have one choice and then one reward, another choice, another reward. It has to be the same. There's a pair. Good. And we could also do the lower range and the upper range for the choice. Lower reward, upper reward. Okay, so those are the ranges. Good. And now the data block is nearly finished, I think. Yeah, it is finished. There is a kind of nothing. Okay, no, nothing is wrong. Good. Then when the data block is finished, we move on or move down to the parameters block. And what parameters do we have? We have alpha, we have tau. Okay. Okay, could anyone tell me how should I proceed here in this case? Any ideas? What are the types of the variables, the two parameters? Do they have ranges? Just think about it in this direction. Yeah, they are floating, yes, real numbers, and they do have boundaries, yes, and how to write it? Remember that? What is the reserved keyword for continuous variable? It's real, right? Real number. And for the learning rate, we have lower equals 0, upper equals 1. For this tau parameter inverse softmax temperature, we have lower equals 0, upper, let's say 20, to be consistent with the literature. Okay. We could comment a little bit, learning rates. Softmax inverse temperature. We don't need to comment anything here because the variable names, they are self-explanatory. They already show, they are already showing what they are, so we don't have to comment. Alpha and tau, if you don't comment, maybe you don't know what I mean. It's better to give yourself a little bit more like informative information for your future self. And then after after the data block and then the parameter block, the parameters block, after they are completed, then what we can do here is we just write down our model block, right? And let's do this a little bit bottom up. So let's say, what do we need? We have this equation first of the value updates, right? Let's write down here. We have prediction error calculation equals the reward minus the V, okay? And then the V, the next one equals, we can just overwrite this one. V, the next one or the new one equals the old one, learning rates, weighted reward prediction error. Okay, good. So these two lines are helpful for us so that we can just implement this idea in a model block, okay? There's a question, what do you write if there are numbers like 1.3 and 1.5, but they are not continuous numeric? 1.3, 1.5, they are floating in floating numeric numbers. You have to still write real, yes, in this case, because they are not integers. Good. So we have multiple trials, right? We have to put or try to run everything in a trial loop. Trial, yes, in an trial loop. We are looping everything from the first trial from the first trial to the last trial. And then inside the trial loop, let's just write down what we have. We have prediction error calculation, just write down what they are, right? Prediction error calculation equals what? Equals the reward, because we do have a variable called reward per trial. Now the trial index, that's very important, minus the value, okay? Good. And then the value is overwritten by itself, and also a learning rate weighted prediction error, okay? So this is just write down what we have. Those are the equations here, and those are the implementation, the span code. Looks good, a little bit. There is a kind of the necessity to introduce a few more variables. So remember the idea that whenever we want to use a variable, we have to declare it. We are now introducing two variables, the PE and the V, right? Without introducing them. So now we have to introduce them. So real PE is just real number prediction error. So real number continuous. And then the value we have to think about that a little bit. Do we have one value or do we have two value? So we have two choice options, right? We have one blue, we have one yellow. So then we actually have to have two values per trial. We have the value of the blue option and also the value of the yellow option, right? Because on each trial, you are choosing between the two options and they have values, both of them, and you are deciding which one is better, which one is worse, and then you make your action. So we do have to have two values in this case. So if we have two values, we can maybe simply have a vector, right? We could have a vector of two elements, like vector, this is a vector of two elements. And we just declare that here instead accordingly. So we have a vector of two elements, V of one and V of two, V of value of blue, value of yellow, okay? V, great. And say you have the observed reward, and then this is the predicted or expected reward, or the value, in other words. Should that be the chosen reward? Should that be the chosen value, right? So if you choose blue, you are expecting the reward of choosing blue. You're not expecting the reward of choosing yellow because you didn't choose it. So here, actually, this means the chosen value. And then how do we implement the chosen value? It turns out that we can use the trial index here. We can use the index of choice as the index of value. So choice per trial, that is just 1, 2, 1, 2, right? choice is left, right, 1, 2, 1, 2. So we use the choice per trial as the index of the chosen value. Does that make sense? So if choice of t is 1, so then this entire thing becomes v of 1. If the choice of t is 2, then the entire thing becomes v of 2. So chosen value. We could even comment on that a little bit. So compute PE for chosen value only. Okay. And the updates follows the same idea. If you choose it, you update it. So the updates only applies to the chosen value. So here we have the same implementation for the chosen value. Okay. Comment a little bit to say, well, updates chosen we. This is the reward prediction error calculation and the value update. Okay, does that make sense? Or good? Or questions?
I have a question about the formula.
Mm-hmm.
We compute the prediction error with a reward minus value and not value plus reward error reward, because the reward can be positive and negative. And if the reward is positive, but the no, wait, yes, if the reward is no, can the value be bigger than 1? Is
No. Mm-mm. No.
Okay, so the reward error, this will still result in positive and negative effects.
Mm-hmm. Yeah.
If you use the value and use plus for the reward, it would still be minus if the reward is negative, right? So do I grasp it wrong, or why do we use?
I see your question. So this one can take two values, either positive one or minus one, right? So it turns out from the math, if you do this kind of calculation and updates, and if the learning rate is indeed a number between 0 and 1, so the resulting value, the value variable, it will be between 0, minus, not 0, it will be between positive 1 and the negative 1. Essentially, it follows the range of the reward. So if you really observe a reward equals positive 1, you will always have a positive prediction error, or maybe 0, because the maximum is 1. So if value is 1, then you have a 0 prediction error. Otherwise, you always have a positive prediction error. Is that your question, kind of?
Yes, thank you.
Yeah, cool. So as a rule of thumb, the range of the value is always between the lowest reward you can get and the maximum reward you can get. Or maybe if this is 2, and then this is 2 here, and then this will just become 2 and 2, okay? It won't be larger and lower than the max and the worst and the lowest of the possible reward in your experiments.
But when the reward is -1 and you subtract another value, then PE will be below -1, right?
The prediction error can change. Yes, the prediction error can change. Yeah.
Okay, sorry.
But not the value. The value is always between 1 and -1. Prediction error can be -1 point something. Yes, this is correct. Yeah. So at some point, let's say if the value is 0.9 and your observation is -1, right? And then your prediction error is -1.9. Yes, this is possible. Yes. So if you're interested in the range of the prediction error is actually -2 to 2. So essentially your largest reward minus your lowest, smallest value. So 2 And if you do the reverse, that's -2. Make sense? Maybe let's write down this a little bit more. So reward can take formally, right? Two values, either -1 or 1. And value belongs to the range of -1 and 1. The prediction error belongs to the range between -2 and 2. Is it better? Maybe that helps. Okay, guys. Good. Okay, good. So when we have all of these elements, what else do we have? We haven't calculated the softmax, right? If you remember, there's a translation from action value to action probability. We need the softmax. So we have two values here. Accordingly, we will also have two probabilities, one for the blue, one for the yellow. We just write down a vector typo here. And how to calculate the value. So value equals, we need softmax, right? So how to do a softmax? Softmax, if you remember, there's an equation like e to the power of tau and then multiply with the value of blue and minus value of yellow and then so on and so forth, right? We don't need it because instead it's a nice language. That's why we're learning it. Softmax is a function instance itself, so we don't even have to implement it. Let's just use what is already there, and we don't have to invent the wheels. The wheels are there. And what is input here? We have the tau parameters, so don't forget that. And we then have the values, right? Here we have the value. So now if we write this way, the tau, the product between the tau and then the v will then be converted to the action probability, which is nice. So we have the softmax converted action probability. So action prob computed via softmax. Okay, good. Last step, we need to model our trials, right? The trials are the real data from the participants. The outcome is not the real data from the participants, because they make a choice and then they see the outcome, and this is part of the experiment. We know as experimenters, we know if they choose blue and what will happen. We know that, but we don't know if they will choose blue. We don't know that, and this is the behavior from the participants, and then this is the behavior we would like to fit. So fitting the model to data, especially in this case, the choice data actions, A, B, left, right, blue, yellow, okay? So in the binomial, well, I told you. So in the globe tossing example, it's the binomial linking function. Binomial is the probability function for that particular likelihood. So I'm telling you that. And for the linear regression model, the likelihood function, what is that? Anyone remembers? We have a slope, we have intercepts, and then we have kind of a noise parameter. And what is the linking, the likelihood, the statistical distribution for linking the known and unknown in the regression model? And that is a normal distribution. So you can just maybe look a little bit more about that. But anyway, we are not using any of them. We are using another one. So we are using something called a categorical distribution. Okay, it's categorical distribution with the P as the input. So what does categorical distribution mean here? And we look at our output. So the output is kind of the choice is distributed as a categorical distribution. So the choices, what are they? Like numerically, they are 1 and 2, right? And can I swap the order such that 1 becomes 2, 2 becomes 1? I guess yes, we could, right? Because blue and yellow, it just can become yellow and blue. Doesn't matter. Those are just two categories. 1 and 2 here doesn't mean 1 is smaller than 2, 2 is larger than 1. There's no order here. It is not a ordinal data. If you like remember what you have learned from earlier study in psychology, there are data types, right? Descriptional and some nominal and ordinal data and like something like that, right? So here the choices are the categorical data. A and B, 1 and 2, they just mean categories. A and B, 1 and 2, they're just arbitrary labels of the two categories. I can even say that one label is -1, the other label is 100. I can just say that because they are indeed arbitrary. So in this case, we are just using a categorical distribution to model the category, how this category are distributed. So here, the action probability, let's say, let's just write down my example. If P equals 0.3 and 0.6, no, 0.7, because they have to sum up to 1. So that means at this particular trial, the model is more likely to predict option or category 2 than category 1, right? So the model is saying, well, the participants is more likely to choose 2. Maybe that means yellow. Good. So here, categorical distribution. Does that make sense? Okay, good. So when all of these pieces are finished, we could be able to test a little bit to check here. If you remember this, there's a checking button at the top right corner. We are able to check if everything is grammatically or syntactically correct. Similar to when you're writing a paper, you have to check the grammatical correctness of your thesis, homework, or whatever. So either English or German, you check the grammatical correctness. So here the same, we are also checking the syntactical or grammatical correctness according to the STEM language features. Did I press? It is just being slow, I guess. Okay, good. But while we are waiting, we do have to have one question. So there is another question that is unsolved. We know that the value are updated, right? We could say, well, value t plus 1 is updated from the value of t, and then the learning rate multiplied the prediction error. Good. This implies that value of trial 3 is updated from value of trial 2, and then value of trial 2 is updated from value of trial 1. But what is value of trial 1? Do we have a starting point? We have not yet defined a starting point. It has to start from anywhere, right? So when we have a starting point and then follows the rule, the choice and action and updates, choice and action and update, it can just go on. It can just go on and on. But where does everything start? Where does everything start from? So it turns out that we could just define the value of blue. I think I told you last time, the value of blue and the value of yellow to be 0, right? Because at the very beginning, if you are the participants, you are sitting in front of a computer, I'm showing you 2 options, blue and yellow, that doesn't mean anything to you. So we can just specify the values of blue and yellow options to be just 0, okay? The initial values. So now what we are trying to do is to specify the initial value, and then the initial value, if you think about that, it has to be declared before the trial loop, right? Because then if you're entering the trial loop, it will just the update will just happen. The update will take place. So the value, we can just write down like 2 zeros, right? So 0 and 0, okay? And you might be wondering, why am I writing a semicolon here? It is because if I declare the value here in this way, vector of 2, it is a vertical vector rather than a horizontal vector. They're not the same. So if we are talking about vectors, there's always the direction or orientation. If I am writing 0, 0, it is a vertical vector. If I'm writing 0, 0, it is a vertical vector, like top down, top down. The other one is left, right, left, right. So this basically means this one has to be matched with this one. Okay, so this is the reason why I have to write like a semicolon to separate the two zeros. Okay, and for a better practice, usually I also write this way. So rep vector 0 twice. Maybe you're not sure if you have to write a comma or a semicolon to separate the two numbers. This is the best way to write it. So you are trying to repeat 0 twice, then it becomes a vector. So rep vector 0 twice. So then in this way, everything is fit to each other. And then up to this point, I guess everything is completed. And if we want to run it, we can run that. But I think my R is super slow and I don't want to run that at the moment. Any questions? So good. Okay. Right. So I think if you have some time, like between today and next Friday, and you could take a look at this R main function, and then to see how we could load our data, and then to run the STEM models. And here is the part to run the STEM model. And if you code your own STEM model, what you can do is you change this one to be the one that we wrote together. You can just change this one to say my first w.span, something like that. Okay. And then this way you're able to just run the models by yourself. And then after running, so here's the part you can run it. And here, this is also the part you don't even have to change because everything stays the same. So because here, those variables are soft coded and they are generic. You don't even have to change anything there. And after the fitting, you could also do the plotting as what we did for the binomial model. And now we could look at how the parameters is distributed. Okay. Any questions here? Good. Oh, good. Okay. So now I'm back to the screen sharing of the slides. So what we want to do now is like, let's say, assuming here's everything that I showed you. So assuming that we just run everything, we run the model, and then what we want to have is the posterior parameter distributions of our learning rates and the softmax temperature, right? So let's think about that a little bit. What do we have for a generic Bayesian equation when we are doing this kind of data modeling? We have the theta given the data. This is the posterior, right? And then this, let's get rid of the denominator because that's not so much important. We have the prior of the parameter, and we also have the likelihood This is the generic form, right? But we now have a more specific example here. What are the parameters? The theta here equals a combination of two parameters. We have the alpha, we have the tau. Tau is the softmax temperature and alpha is the learning rate. And what are our data? And we have the choices. At the same time, we have the reward, the corresponding reward. So if we are maybe rewrite our posterior Bayesian equation, what it becomes, it now becomes like this. So our posterior is what's the posterior distribution of alpha and tau is given the choice and the reward of the participants, okay? And then this follows the rule, like you can also write it down, but we can just get rid of it because this is rather easy. Here, basically, the prior means the P of alpha comma tau. Here, the likelihood means the P choice comma reward, like also there's a bar, then alpha comma tau. That is straightforward. So here, this is more important to have an understanding of what we actually want to have. This one, if I erase all of the others, this is our target. This is the posterior parameter distribution that we would like to have. And this is the results that we would like to achieve using the Markov chain Monte Carlo, right? So the posterior distribution, eventually, how does that look like? This is already shown on the graph. And this is the posterior distribution of alpha, learning rate parameter, and then this is the tau parameter, okay? So both of them too together. Those are the results that we would like to have. Great. Does that make sense? Okay, I guess that makes sense. Good. And a little bit next is like conceptually, we don't have one participant, right? What we have multiple participants. And usually, how do we fit the model to the data when we have multiple participants? There are multiple ways from the literature, and there are pros and cons of those a few approaches. Let me just introduce them to you one by one. So the simplest approach is like as if all of the participants, they are a single person. So we recruit, for example, if we recruit 10 participants to do the experiments and we are fitting them together, and we could fit the data as if this is the same person, it comes or he or she comes to the lab 10 times. So the assumption here is rather strong to assume that these 10 people, they have the same learning rates and they have the same softmax inverse temperature, right? So here, if you look at the graph from like this graphical model, what is added from the previous version is, let me change a different color. The newly added element is this kind of subject loop. There is another loop, but at the same time, the two parameters are outside the subject loop, which essentially means all of the 10 participants, they are having the same learning rates and the same tau, okay? So maybe you think this is stupid because why those 10 people, they have the same learning rate and the same tau, but from the literature, like earlier, like maybe more than 10 years, people do this one, they do practice this kind of model fitting because that's easier. And also because back then fitting model, the machinery is also not so powerful relative to the ones that we are using today. So this is like a little bit easier and also cheaper way to achieve some data results. And you are smart enough and you would imagine that why not all of the 10 people. So here is how that everything is implemented. We are just adding a subject loop, nothing else. So you are smart enough, and you are also imagine that why we would treat all of the 10 people as if they are a single person. Can we fit the data independently, right? So before we run that, or before we conceptually introduce it, we could also see some comparison. Either we just run one person versus we run like the data from 10 people. Maybe there's a quite striking observation, that is the variance is getting smaller, right? Because we have more data and then the variance, the uncertainty is reduced. So let's say if we are trying to run all of the 10 participants all independently. So here again, this red circle, that is the subject loop, but instead of all of the 10 people, they have the same learning rate, they have the same softmax inverse temperature. Now these two variables, they are inside the subject loop, and we are also having a subject index here and here, meaning that if we have 10 participants, we will have 10 of the learning rates and 10 of the softmax inverse temperature parameter, the tau parameter. So essentially, this means all of the data are fitted independently. So they have their own individual difference, and everyone could have their own learning rates and tau parameter, softmax temperature parameter. And implementing this is also not so much work. So we have the subject loop, we have the trail loop, and everything is nearly the same as before. So what is added is only the subject index of the two parameters. So before we only have tau and alpha, but now we have the trail, we have the subject loop of the two parameters, indicating each time within the subject loop, there is a subject specific parameter, tau and alpha. Okay, does that make sense still? And here is kind of a result of fitting the data from 10 participants and see how the result could look like. And we're able to tell that you see that some of the participants, the learning rate is around like 0.5, 0.6, and some of them, the learning rate is a little bit higher, and some of them, the learning rate is a little bit lower, okay? There are some like variance here. For the tau parameter, same thing, and some of them, they might have a larger tau, which is larger, this one is a larger one, and for this one, the tau, this person, the tau is a little bit smaller, okay? And then here, maybe you don't really show this kind of graph in the paper because people don't really run participants from 10, people don't usually run experiment from 10 participants. This is too few, and we could run maybe 30, 40, but imaginably, if we run this kind of analysis, if we show the data from all of the 40 people, this can be just a rather long, lengthy graph, which is also not so easy to read and not so too noisy and too busy, and you can't really show what you really want to tell to the readers. So instead, how do you summarize this kind of results? What you can do is to use a plot, a specific plot that is called a violin plot, because the shape of this plot looks like a violin, right? This one. So especially this one. How to read this kind of violin plot? I'm not sure if you have if you have seen this one. Have you seen the violin plot before? Just tell me in the chat, yes, no. So the violin plot basically shows, it's a combination of density plot and a box plot. So we know box plot, right? So here, let's say I show you a box, and then like this, roughly. Maybe also like this. This is a box plot. You know box plot, right? So here, this one depends on how you specify that. It can either be the mean or the median. And then this may be 70% quantile. And then this is the lower bar is 25% quantile. The lower and the upper like edges of the box. And then here is maybe the standard deviation and or the standard error, depends on how you specify that. Okay, this is the box plot. And then what is density plot? So if you have individual data points. You have some of the data points here, and then a lot of them in the middle, and then a few guys here and there. You have a lot of guys in the middle, a lot more. Okay, good. And one way to like kind of summarize this kind of distribution, because if you have a lot in the middle and not so much before and after, like lower and higher, you could imagine there is a distribution, and in the center the distribution is higher or taller, and then the two ends not so much happening. You could derive or estimate a density from all of the individual data points. So here you estimate the density from this individual data points, okay? And the box plot is like the same. There is underlying raw data somewhere. Okay, good. Good. So if we say, how about combining the box plot and the density plot, then the resulting one is the violin plot. So here, if you turn this density like 90 degrees counter the clock, then that is just like a vertical density. And then on top of that, you superimpose the box, then it becomes the violin plot, right? So here you can just take a look at, maybe it's the first, the left hand side. That is enough because the entire thing is symmetrical. So here you could imagine there are individual points, data points, not so many up, not so many down, but a lot in the middle. And you're trying to estimate density. And then this is the average. There's the huge black dot, that is average. And then here, depends on how you specify that. That can be maybe the standard error. And here, these two can be like the 70% and the 25% quantile, respectively. So essentially, this is a combination between the box plots and the violin plots. Okay, this is really nice to show a summary of individual data points, better than each of them alone. So because that is a combination, it takes the advantage of both of them. That is a better one. Good. But why the other one? Why this one doesn't look like a violin? It is because the individual data, they do not really have a stronger cluster effect, because nearly everywhere is the same. Everywhere there are data points. And if you try to estimate the density, you can't really show much, just flat, right? Flat. So it doesn't so much look like a violin, but it is still a density plot. Well, good. So the next thing that I want to show you is like, well, because like those are those are the results from 10 participants. And where does the data come from, those 10 people? And those 10 people are actually not real participants. They are simulated data simulated by myself, so that I know what the true parameter is. And if I compare the estimated estimated parameters on top of the true parameter, you don't really see so much overlapping, right? You see, well, maybe the magnitude here, this is relatively the same. This is also roughly the same, a little bit higher, but the distribution between these two and then these two, especially here, the top parameter, they don't look so much alike. So why there it is the case? Why here, especially for this parameter as well? Why in these two cases the variance is larger than the original one? It is because we are treating all of the participants all independently, meaning that they do not share information among each other. But actually, when we are running experiments, we recruit real people, it is very likely that they are coming from the same population, right? I'm not saying that all of them are just students between 18 and 25 years old, but let's say healthy young adults between 18 and maybe 35. Some of them maybe still studying, but some of them, they are having some other jobs. Just normal everyday life, healthy participants, right? There might be some commonality because they are coming from this large population. So is there a way that we could consider both the commonality, assuming where they are coming from, and also the individual difference at the individual level? So can we combine both information? So the answer here is yes, we can do that. Let me just have a quick introduction to that part, and then we can finish, we can wrap up, and then we can resume this discussion the next week. So there is one idea of coding to implement this idea of combining both the group level commonality and the individual level difference. Because there's the hierarchy up individual level, then it is called hierarchical model. Or in some other literature, it is also called multi-level model because there's one level, group level, and individual level. It's just individual level, multi-level modeling. Okay, similar idea. And let me first show you this one. Let me show you this one. Assuming that those are the data from a experiment. So they are just healthy young people, male, female, mixed. They do have commonality and they also have individual differences. The previous approaches to fit multiple participants that I showed you is, for this one, we are treating all of the individuals as if it is a single person. And the second approach is like we are fitting all of them all independently without letting the mutual information flow within this data fitting scheme or like data fitting framework. All of them, both of them are not ideal because this one is obviously so biased, right? We are considering those individuals as if this is one person, and the other one is sparse, and all of the commonality information is lost in this process. Solution is also obvious. We just combine both of these two. So how to combine that? By introducing another layer. So that's how come we have a hierarchical modeling, another layer, another hierarchy of data fitting. So we are trying to introduce the group level distribution, assuming all of those individuals are coming from this group level distribution, assuming they are coming from the same group. This is usually a okay hypothesis because if we are indeed testing healthy young adults, there is a healthy young adults group. But if we are doing perhaps between subject design, we could imagine that there are two groups because one group is maybe the treatment group, the other one is the control group or maybe placebo group. And if we are doing also clinical research, we have the healthy control, healthy population, healthy group. We have some patients group, for example, Alzheimer, for example, like depression or stress or anxiety, whatever, you name it. Those are different groups. And we could, in all of these cases, introduce the corresponding group level distribution on top of the individuals. And this is this makes a lot of sense, right? Because there is indeed a group, either experimentally manipulated or comes from their specific population. So this is so far the best approach. And many people are appreciating and practicing this hierarchical modeling in their data fitting procedures. And many of them are achieved. This is also helpful to achieve a lot of statistical power because it considers the structure of the data. So all of the technical details I will skip, and I will just introduce you a little bit more of that. So the hierarchical modeling, for one, that makes sense. For two, it actually is much reliable in terms of the parameter fitting. So here I'm showing you three lines or three curves using simulation. So if that is simulation, then that means we also have a true value. So here in this black circle, this curve, that is the true value. And then we want to do model fitting to try to recover if we're able to find out what the original parameter is. And we are comparing two parameter fitting methods. One is the hierarchical Bayesian methods, the hierarchical version. The other one is the maximum likelihood estimation without even considering the hierarchies. So here what you can see is that the triangle is not really following the black circle, right? But if you are comparing the black line, the black curve, and the blue curve, you are seeing that these two are pretty much the same. They are resembling each other. So this means if we are using the hierarchical Bayesian approach, in terms of the accuracy and the reliability of parameter estimation, it is also outperforming the more traditional non-hierarchical and maximum likelihood estimation. So all of this, I'm trying to convince you that hierarchical modeling is the best approach in this field. Not only cognitive modeling, but also when you are fitting a regression model, you are also able to use hierarchical modeling, right? And then the details, let's just talk about that next week. Questions?